Welcome to another very normal therapeutics training video. In this video, you'll learn about confidence intervals. If you're new here, I'm Christian and this is Very Normal, a channel for making you better at statistics. I don't actually have a pharma company, but I like to frame my explainer videos as employee training videos. Thanks for tuning in. When we conduct hypothesis tests, we ultimately make our decision to reject or fail to reject the null hypothesis based on the p-value, or at least that's what Fisher would have wanted. But in reality, we have other metrics we can use to make this decision. These metrics were the contributions by statisticians Jerzy Neyman and Egan Pearson to the Null Hypothesis Significance Testing Framework, or NHST. If you need a refresher on that, refer to past training videos. One of Neyman and Pearson's contributions to the NHST was the idea of the alternative hypothesis. The alternative hypothesis opposes the null hypothesis, and it typically represents the point we want to make. In a two-sample t-test, the usual null hypothesis is that there's no difference in population means, so the alternative hypothesis is that there is a difference. Depending on what we think about this difference, we can get different alternative hypotheses. The most common alternative hypothesis is what's called a two-sided hypothesis, which arises when we don't want to assume any particular direction for the difference. We just think it's not zero. There are also alternative hypotheses that suggest the difference is greater than or less than zero, and these are one-sided hypotheses. For simplicity, we'll focus on the two-sided case. The alternative hypothesis actually isn't needed to make the decision about the null hypothesis, but I need you to know it for future training videos. The null hypothesis can either be the true state of the world or not. We don't know which one is true, but we ultimately have to make a decision to reject it or not. This sets up a confusion matrix. We'll focus on this side of the matrix where the null hypothesis is actually the true state of the world. When we fail to reject the null hypothesis when it's actually true, then we made the right call. But if we decide to reject it when it's actually true, then we messed up. There's a specific name for this type of error, a type 1 error. In a two-sample t-test, a type 1 error is concluding that there is a difference between two groups when there actually is none. Neyman and Pearson approached the decision-making process from the perspective of type 1 error control. Before we collect any data, Neyman and Pearson tell us that we can change how tolerant we want to be of type 1 errors. Let me explain. Let's say our pharma company finally develops a new medication for treating high blood pressure. This medicine only causes light side effects, like a small headache. To give this medicine to humans, we have to prove that it's superior to a placebo. For a relatively harmless treatment like this one, type 1 errors aren't too consequential. Even if it doesn't actually work, it won't cause much harm through its side effects. But what if our new medicine actually had severe side effects? Severe enough to actually hospitalize you? We shouldn't be so relaxed about accepting a type 1 error. If we're actually going to give this to people and subject them to severe side effects, then we'll want to be really sure that we're not committing a type 1 error. Neyman and Pearson's error control approach allows us to consider this when we do a hypothesis test. Let's visualize the null distribution of the t-test. As a probability distribution, it tells us what values are possible under the null hypothesis and the probability density associated with these values. These low regions tell us that it's still possible to observe extreme differences between the two groups, even under the null hypothesis, but they're just really unlikely. We should ask ourselves, when is an extreme value so extreme that we should reject the null hypothesis? Neyman and Pearson's approach divides the domain of the null distribution into two regions. Once a test statistic is extreme enough, then we should reject the null hypothesis. We'll call this region the critical region. In a two-sided test, we don't assume whose group mean is higher, so this region is defined by 2 points, one for extremely low differences and another for extremely high ones. We'll call these 2 points critical points. Once we actually collect data and calculate a test statistic, we can check if it falls within the critical region. If it does, then we reject the null hypothesis. If it doesn't, we fail to reject. But this brings up another question. How do we decide the values of these critical points? Neyman and Pearson want us to declare a maximum level of tolerance that we have for type 1 error. We call this the level of our test. This is slightly different from the significance level described by Fisher. It's usually 5%, but if we want to be especially strict on type 1 errors, we can choose something smaller, like 1%. Let's say that we'll tolerate a 5% probability of a type 1 error. To decide our critical values, we need to choose two values such that the probability of observing these values, or something more extreme, is equal to 5%. In other words, the area past these critical values should be 5%. Why is this? As I've mentioned before, it's still possible to observe extreme differences between two groups, even when there's no true difference between them. If the null hypothesis is true, and our data produces a test statistic that falls within the critical region, we have to reject the null hypothesis, and this results in a type 1 error. Since critical values here are defined by how much probability is before or after them, by definition, these values are percentiles. There's usually no reason to bias one side over the other, so we usually divide this 5% equally between the two sides. Thus, the critical values are the 2.5 percentile and the 97.5 percentile of the null distribution. If we choose our level to be the same as our significance level for a p-value, the critical region method and the p-value will come to the same conclusion. With that being said, we don't usually report critical regions when we write about them in statistical analyses. We usually report confidence intervals instead. But where do confidence intervals come from? I'm going to talk notation a bit, so if you don't like mathematical notation, take some time to get mentally ready. We learned earlier that the two critical values are the 2.5 and the 97.5 percentiles of the t-distribution. Let's say that this capital T represents the test statistic for a two-sample t-test under the null hypothesis. By definition, the probability that our test statistic will fall outside these two percentiles is 5%. Conversely, the probability that it will fall between the percentiles is 95%, and this statement will be our starting point. Instead of writing it as a capital T, we'll replace it with our standardized difference in means. The standard deviation is really messy to look at, so I'll replace it with some simpler notation. Notice that we have a function of both population difference and the sample difference in the middle of this probability statement. Using some math, we can isolate the population difference in the middle, and it leaves us with this expression. What we've done is shift the random variables from the middle part of the inequality to the ends, leaving the population difference in the middle. This is important. Note that nothing we did influences the fact that this overall probability is still 95%, but it changes how we interpret this probability. We can interpret it in terms of the population mean instead of the test statistic. And it's still a probability statement because the ends of these intervals are still random variables. In simpler terms, the probability that the true population difference falls between these two values is 95%. This is what we call a confidence interval. Instead of totally not knowing, we can use data to construct a range of possible values. But confidence intervals aren't intuitive tools. Confidence in a statistical sense doesn't have the same meaning it does in everyday conversation. Since the ends of the confidence interval are random variables, it means that the endpoints can change depending on the data we collect. Once we actually collect data and calculate a test statistic and a confidence interval, only two things can happen. Either this calculated interval contains the true population difference, or it doesn't. There's no way of knowing if the one we got actually contains the population difference. To understand what confidence means, we have to calculate many confidence intervals from many data sets. According to this statement, 95% of the intervals we create will actually contain the population difference. Therefore, we are 95% confident that our interval will contain the parameter of interest. This idea of collecting many data sets and making many intervals is what frequentists sometimes call behavior in the long run. They're useful because they constrain the range of possible values, but they're also not useful because we can't know if our interval actually contains it or not. Since we use the critical region to decide whether to reject or fail to reject the null hypothesis, by extension, we can use the confidence interval to do the same thing. From the perspective of the critical region, we focus on the test statistic. But from a confidence interval perspective, we need to think about the null hypothesis. If the value of our null hypothesis is within the confidence interval, then the confidence interval suggests that the data we collected could possibly come from a world where the null hypothesis is correct. If this happens, we have to fail to reject the null hypothesis. There's a clear relationship between our tolerance for a type 1 error and the confidence for a confidence interval. It's common to denote our desired level for a test as alpha. To create a confidence interval of a desired confidence, we need to look at the area between the critical values, so the confidence level is 1 minus our level, or 1 minus alpha. If we wanted to make our test stricter and use a 1% level, then it means we'll make a 99% confidence interval from the critical region. From our perspective as the statistician, we'll never know which hypothesis is actually true, but the fact that it's possible for the null to be true means that we have to account for it in our decision making. Statistics is the study of data, which means we must always cope with uncertainty. Neyman and Pearson's approach at least gives us some agency to adjust how we make decisions about our null hypothesis. Fisher, Neyman, and Pearson all contributed to the NHST. If you're doing a hypothesis test, then make it a point to convey everything you can about the results. This includes the test statistic, the confidence interval, the p-value, and your chosen level of the test. Providing all this information gives full transparency and keeps you honest in a statistical sense. And that's it for this training video. Consider subscribing to the channel and maybe even the newsletter. Thanks for watching and see you in the next one.